Awesome. Well, take it away whenever you want to.
All right. Okay, you can see my screen now?
Yes.
Cool. Okay, well, thanks for the invite. I really appreciate the opportunity to chat with folks here. And like I mentioned, I'm happy to make it more of a discussion than a presentation. So if there's questions, feel free to interrupt me along the way. And again, thanks for having me. It's great to see so many friendly faces, and hopefully we'll get to go out and see you guys in person soon. So what I'll talk about today is a review of developments in nonlinear optimization of electric power systems. So my goal is to have more pictures than equations, and I'm pretty sure I've met that. But if you want me to go more in depth in some topic, just stop me and I'll be happy to talk about it for longer than you probably care to hear. Okay, so first a little bit of motivation. Why do we care about optimization in power systems? Why do we need new computational tools? It's in large part due to the underlying changes that we're seeing in power grid operations. So I think this audience knows these, probably knows this story well, but just to get everyone on the same page, what we're seeing as we look forward is massive retirements of controllable generation of coal and nuclear and a lot of older gas units, while at the same time we're adding on a lot of uncontrollable generation, lots of wind and solar, which is great environmentally, but has some challenges when it comes to controllability. And what's the challenge in doing that? Well, we have to integrate this all into our legacy power grid. Here's the high voltage transmission network in the US, and this was not a system designed for the purpose of integrating renewables. It takes a long time to build new transmission lines, and so we sort of have to work with what we've got. And what's the difficulty in doing that? Well, there's a lot of variability and uncertainty that we're introducing into the system operations. Here's a typical day of solar PV generation. It gets cloudy. The sun, the solar power is hard to predict. Although I have a student in my class, my undergrad class, that's a former Air Force weather forecaster. And he tells me they're getting better at these things. Really interesting background. He worked in your neck of the woods. He did the forecasts for Southern California and the West. So learn a lot from him. Anyway, so the story is we need new computational tools to economically and reliably operate electric power grids when we have lots of renewable generation. And so at the heart of almost all of our optimization and control problems that we work on in power systems, we have some representation of the powerful equations. And so these are the equations that model the relationship between the voltage phasors and the power injections in the electric power grid. So here's one representation of these equations. Turns out there's lots of mathematically equivalent ways to write down the powerful equations. And you can actually get very different behavior depending on how you approximate or relax or represent the powerful equations in different coordinate systems. This is probably the most common representation, is to put the voltages in their polar coordinates, so a magnitude and an angle, and then we get these coupled relationships between the active reactive power injections, the voltage magnitudes, and the phase angles. And so these equations are in almost everything we do in power system optimization control, optimal power flow, unit commitments, voltage stability analyses. Almost any problem that you care to solve will have these equations embedded somewhere. As one prototypical example, we've got the optimal power flow problem, or OPF. This is a very stripped down version of this. I'll talk about some more sophisticated forms of this problem in a few minutes. But typically what we want to do is minimize the cost of generation. We have a set of engineering limits where we can't operate our generators outside of their upper and lower bounds. We want the voltages to be within reasonable ranges, and we have to make sure our line flows are within their limits. And then we have these powerful equations, the equality constraints representing the actual system physics of the power system. And so, this is a hard problem, or can be a hard problem. People claim it's a hard problem. What does it mean it's a hard problem? Well, at least in some instances, you can have cases where the feasible space of the OPF problem is disconnected. So I'm an engineer, I like making pictures. And so we took some of these hard examples, or examples where we knew that there were local solutions, and plotted them. So here's one example. This is a 5-bus system. It's got 2 generators. What we're showing in this figure here is on the horizontal plane is the active power output of the 2 generators, and the vertical axis is the reactive power output. And this feasible space, if you make a projection of this, it looks like a Nike swoosh. And it turns out if you enforce a lower reactive power limit on this generator 5, that lower reactive power limit is the gray plane, and it slices off the bottom of the Nike swoosh, and you're left with this global solution and this local solution here in the green star and blue triangle. And so this actually isn't too atypical. I'll show another example in a second, but what you have going on here is voltage and reactive power limits that are, the lower voltage limits are defining the bound on the upper part of the Nike swoosh. And so then the reactive power limits comes in, and the interaction of those two limits oftentimes is what leads, at least in the examples that we're able to generate, tends to lead to these weird feasible space characteristics. Here's another example. This is a 9-bus system. It is the IEEE 9-bus system, just with modified power demands and modified reactive power limits. And the feasible space for this problem is disconnected. You've got these 3 disconnected regions here. In the normal 9-bus system, this is just a filled-in triangle. And so what happens is by playing with the reactive power and voltage limits, you can sort of slice out this oval from the middle of this triangle, and that cuts the region into these 3 different pieces. And in this case, it turns out there's the global solution and then 3 local solutions. Oh, and I should clarify, the local solutions, by that, what we mean is a solution that's superior to all the nearby points, but is inferior to some global solution, the best operating point further away. And so at least in principle, these problems can be quite hard to solve. And so what do people do instead? Well, what's commonly used in practice is in many applications is this DC power flow approximation. Again, I suspect most folks are very familiar with this. This is a linearization of these nonlinear power flow equations that's applicable to typical transmission systems. And so what we do is we say, well, let's just completely ignore reactive power. That's someone else's problem. Someone else is another engineer that has to make it work later. But for now, we'll ignore the reactive power. Then we're just left with this active power equation. And in typical transmission systems, we try to keep our voltages close to their nominal values. And so if we normalize those appropriately, we can set those to 1 per unit. We still have a nonlinear system of equations through these trig functions. And so we say in typical transmission systems, let's neglect the resistances or the conductances, depending on how you want to exactly do it. Here we'll neglect the conductances, and then we can set this cosine term to 0. It's still nonlinear because we have the sine function. And so what we can do instead is replace the sine using the small angle approximation with its argument. And you go through all these approximations, and what you get here is this the textbook version of the DC power flow equations relating the voltage angles linearly to the active power injections. And so this is, a bit of a straw man. In practice, what folks in the industry will oftentimes do is do much more sophisticated versions of these DC approximations. They'll build in loss approximations. They will adjust for maybe different voltage magnitudes. And there's lots of ways you can play with these equations to maintain linearity while still just having, that are related to this fundamental relationship. But this is what we teach our students, at least. Lots of advantages in doing this. We have fast and reliable solution methodologies using linear programming. But on the other hand, we just don't consider voltage magnitudes or reactive power at all. And so any analysis dealing with voltage stability or reactive power margins or anything like that, you just can't use this approximation. And there's just inherently some approximation. And so when you're operating a $400 billion a year system, you'd like to minimize it. So, but this again is a bit of a straw man, but basically our current practice is to do something like this. We do all of our analyses using this DC power flow approximation. We put it into this black box that's called engineering intuition heuristics, which is our system operators and other engineering analyses. And out comes some feasible point to operate the AC power flow that satisfies the AC power flow equations and is acceptable for operating the system. And this works. The lights are on, at least they are here. But it'd be nice to, the whole history of what we've seen is in power systems and other domains is the more we can build the actual physics into the problem we're solving, the better off we can be in terms of getting high quality solutions. Okay, so that's the setup. There's the motivation. So what have people done to try to handle these nonlinearities? And I posit there's really 4 different approaches that people have taken. The first is to use local optimization techniques. This I'll go through in detail. Here's my outline slide. I tell my students not to have an outline slide. This is my outline slide for my talk. So, one approach people have taken is local optimization. This has been really successful or proven its value in this recent Department of Energy RB grid competition. I'll get into some more details about that. But almost all the top teams were using some sort of local optimization strategy at some point in their algorithm. And so what you do here is you start at some initialization, you try to locally improve your solution until you get at least to a local optimum is the goal. Second approach people take is approximations. Oftentimes they're linear approximations because we like linearity. So this is like the DC power flow as one example. We take our nonlinear equations and we use some form of linearization. Okay. So local optimization strategies. These general class of approach tries to find some operating points that's superior to all the nearby points, but has no guarantees with respect to more distant operating points in parameter space, or in the space of generator set points. And so these are inherently dependent on the initialization. So if you imagine if my cost function is decreasing or improving and down to the right, if I initialize here, well, then I'm pretty likely to find a point that is is the best solution to this problem. But maybe if I initialize somewhere else, I might get stuck in a local optimum. And so that's sort of the inherent downside of using the local approach. But oftentimes it can be fast and reliable, and there's well-developed methodologies for using this. So we're trying to find global solutions. Oftentimes we actually do find global solutions, but we might get stuck in a local solution. And the likelihood of that happening really depends on the problem characteristics. So it's hard to say in the abstract whether you'll find the global solution or you'll get stuck. There's two main classes of tools that people use for local solvers. One is interior point methods. The most famous of these is IPOpt, interior point optimizer. It's an open source package. Another one is sequential quadratic programming methods. One of the more famous ones on this is SNOpt. Now, one thing I want to highlight with, so interior point methods can be somewhat difficult to initialize. This is one of their main disadvantages is even if you have a really good solution or a good estimate of the solution, oftentimes these interior point methods, they use a barrier function that sort of pushes you away when the algorithm starts from the boundary and then sort of circles back to the actual solution as the algorithm proceeds. So this is one of the really frustrating things with an interior point method is I have the solution out to 3 digits of accuracy, and I'm trying to just update something and make it try to converge to a really nearby point. That doesn't mean it's going to do that. On the other hand, it can be really fast and really effective. We'll see. This is the method that a lot of teams used at least all the teams that I know of that did well used this approach in the grid optimization competition. Now, another approach that people use is the sequential quadratic programming. This is probably what's more familiar to power system engineers. It certainly was the way I was taught about power system optimization initially was, well, linearize the nonlinear equations, solve the LP, update by solving, the power flow equations again to make sure that you get a feasible solution and iterate on that process. Now, that's how I learned sequential linearization style methods. Turns out I've been talking with folks that, the developer of SNOpt, for instance, there's a lot that actually is much more sophisticated than that can go on behind the scenes here. And so I see this from students quite often is that they'll say, oh, well, I did a sequential quadratic programming method. I say, well, okay, what did you do? And they said, well, I just left the objective function quadratic. I didn't linearize the quadratic in the objective. And so it's sequential quadratic programming. I mean, that's not entirely wrong, but that's really not what they do in sequential quadratic programming is they have a Hessian, they consider the Hessian of the Lagrangian. So it's much more of a sophisticated method than you might have learned as a first-year graduate student in power engineering. So dig into this a bit more if you want to go in this direction. This does initialize well, but can be slower if you don't have a very good initialization. That's a very high level overview of nonlinear optimization. So where was this used successfully? So Department of Energy had this grid optimization competition. The first round of this competition completed last year, right before the pandemic. And now we're in the second challenge going on now. That'll end this summer. This problem was to solve security constraints, AC optimal power flow problems, where the goal is to jointly optimize the generator's real power outputs and the voltage magnitude set points of the generator. So this is not what they do in practice today with the DC power flow. It would allow you to really have a lot more flexibility in modeling this problem. And at the same time, you're asked to solve, or you're tasked with solving basically N-1 preventative security requirements. So if any one thing in the system failed, this operating point had to adjust in a pre-specified adjustment to still satisfy the constraints in the problem. And so this problem gets really big, really fast. So the objective function, they had a piecewise linear generation cost. That wasn't too terrible to deal with. And then you had a base case where you had voltage limits, line flow limits, generation limits, AC power flow equations with all the components in service. And then you had a set of contingency cases where the information that was transferred back and forth between the base case was the nominal set points for the generator's active power outputs and voltage magnitudes. That was the same between all the contingencies. And then the contingency cases were after the failure of one generator or one transmission line or transformer. So this is, if I just showed you this is a pretty typical formulation that people consider. Where this got a lot harder in the competition was dealing with additional nonlinearities. So you had complementarity constraints from both the reactive power limits. So basically the voltage magnitudes were fixed from the base case until you hit upper or lower reactive power limit, at which point the voltages were allowed to decrease or increase. So this is the typical, PV, PQ switching style characteristic you'd see in a lot of power system textbooks. And then on the same time, you also had real power limits where if a generator, so we had a participation factor model, or the competition had this participation factor model where you had these participation factors alpha, and all the generators responded proportionally. It was effectively an affine control strategy, similar to a model of AGC. Until you hit a power generation limit, at which point that generator stopped responding to the AGC signal and just was fixed at its maximum output. And so this was difficult to deal with because you had these additional nonlinearities along with the power flow equations that you had to handle. And so to summarize here, the challenges in this competition were the problem size. So there were systems with up to 30,000 buses and close to 11,000 contingencies. You had nonlinearity from the AC power flow equations. You had these complementarity conditions from the generator limits, and you had to solve it all in 10 minutes or 45 minutes. So it was a hard problem. And so our approach, so I was on a team called Team GhostNip. It was SN was for SN opt and IP was for IP opt, because we had the developers for both of those on our team. Sorry, that's my wife's phone in the background. You get it, Arjun? So our general approach is laid out here. We had a pre-processing step where we tried to identify the key contingencies, so a contingency screening of contingencies that wouldn't be relevant and try to rank the most important contingencies. We then solved a base case problem. We used IPOpt for this. We had Andres. So Andres Vector is the developer of IPOpt. So he was on our team, so we first used IPOpt, but so did everyone else. So Andres gets a lot of credit for this. Andres is really shy sometimes when he's presenting. He doesn't take enough credit for it. IPOpt is fantastic. It's used by everyone. It works very robustly, and so you should get a lot of credit for this tool. We then went into an initial contingency ranking phase. Using the base case solution, we tried to identify which contingencies were most important. We then select the contingencies from the top of this ranked list. From that, we could solve the master problem, the base case, plus a selected set of contingencies, and we, again, did this with IPOpt. From there, we kicked off a parallel evaluation process for all the contingencies to try to start evaluating all 10,000 or so of these contingencies. And we could do that in parallel. They actually gave us quite a few computational resources to use, so parallel processing was key to this. And then we would iterate back and forth between solving the base case and the selected contingencies and adding in new contingencies, the most violated contingencies that we found. And you iterate on this process until You know, you either run out of time, converge, or more likely you run out of time. And so one of the things I want to point out here is the local solution techniques were really key to this whole process. IP-opt is used at almost every stage of this solution methodology. And so what were the results of this competition? Here's my summary of the competition. So the top teams were able to reliably output solutions for large-scale problems with low generation costs and small constraint violation penalties. So my message to, there's no one, I suspect not too many industry folks here, but my message to people in the industry is this works. You know, not just our team, but other teams, you can solve large nonlinear problems and get better solutions than you would get if you just applied a decent power approximation. So we should be doing this, is my takeaway message. How did local optimization do in terms of these problems? Now, here's the top teams. I'll brag for a second. We got second. So this is myself and Andres and Armin at Northwestern, and Elizabeth at UCSD, and Frank is at Lehigh. Really fantastic work with them. And so a couple of takeaway messages I took from the competition. One was, and first of all, relevant to this presentation, IP-opt was used, I know, by at least 4 of the top 5 teams. Different problem formulations, different strategies for using it, but they were all using some form of local solver. And I suspect actually more of the teams were as well. I just don't know exactly what. The second takeaway message I'd mentioned from this is, if you look at a lot of the top teams, it was involving folks with both optimization experience and power systems experience. Either optimizers with power systems experience, power systems folks with optimization experience, or mixes of both. And so that was really crucial for this competition. Was you needed some power systems expertise, but you also need a lot of expertise in optimization, the theory side of it. You needed folks that knew the numerics really well. You need people that could program, especially large-scale parallel HPC style computing methods. It really was a tour de force in terms of the expertise you needed for these sort of problems.
Dan, could I ask a question
Sure.
about these IP-opt? Is your impression that the reason IP-opt was so successful that it was faster, basically getting to a critical point or a local minimum, or that it was able to, the interior point aspect of the optimization algorithm actually steered it away from certain local minimum towards a global minimum?
So this is a really good question. And I've talked with Andres about this quite a bit. And I asked it because IP-opt, it just works so well. Like, it just defines, it's robust. It defines, oftentimes the global solution to the problem, even though it doesn't have a guarantee. And I asked him, like, what's the magic sauce inside IP-opt? And I mean, it's well implemented. Andres is a fantastic coder. It's very robust software. And so from that perspective, that's one reason why it's so valuable. The other perspective, though, was, so I asked, is there something special going on? What's your little trick that you use inside of your interior point method? The answer is nothing. There's nothing special. It's a standard interior point method. So it's possible. This is something I think is not well understood, is whether there's a couple of things that can be happening. One is the problems are, at least these sort of practical problems, there just aren't that many local solutions. And so there's not too many ways to get stuck. I know there's a lot of critical points. We did some analysis on that years ago. But maybe there's just not a lot of local solutions. That's possible. It's also possible that something about the interior point method or the initializations we use for it are good enough to sort of miss the local solutions that do exist. And I sort of suspect it's some combination of both of those things. But that needs, I would love to study that. That's a grant waiting.
Okay, thank you.
Yeah. Okay, so yeah.
Can I ask one real quick question?
Sure.
So I'm wondering what kind of programming language you use for building the whole software. Number 2 is if you have any plan of open sourcing whatever the software that you develop using IP-opt. And number 3 is, are you testing this for the IEEE test cases, or you have planned to extend it for the real world cases, like typically what happens in a production cost modeling, where you take into account lots of different factors in types of generators and all sort of things, and do an actual simulation for like the day ahead dispatch, let's say.
Sure. Yeah, no, all good questions. So let me try to remember all of it. first of all, so we programmed it in C++. I'm not good at programming in C++. So when I say we, I should say Andres and Armin and Frank and Elizabeth programmed it in C++. That seemed to be the case for most of the top teams. I know Cosmin, they I believe programmed in some low-level language. I thought it was C or C++. I think Andy did the same thing. Some of the other top teams, so Gravity, so Hassan and Nathan Lemons, they have their own modeling language. If you're not familiar with Gravity X, it's a really cool tool that Hassan put together for solving a modeling language in C that is fast, and Hassan says great things about it. I'm just not good at programming in C, so I'm not. It's not my expertise. But yeah, so I think a lot of folks used as close to the iron as you can get. Let's see. Your second question was, I forget your second question. Actually, I forget what were your second and third question?
The second question was like, if you have any plan of open sourcing the whole model, like really open source license. My third question was if you have plan of using this model to solve like real world system, taking.
Got it. Yeah. And, okay. So in terms of open sourcing,
actually, when you mentioned about C++, I just remembered one other follow-up question, just in case if you have any thoughts. What about using something like Jump, Julia?
Yeah. So I mean, we're familiar with Jump and Julia. Andres doesn't like it. He likes programming as close as he can to managing the memory himself and sort of doing all that work himself. I'm more than happy to use Jump and Julia and Power Models and all these fun packages that are in there for my own research. And I have students using it as well. For this team, that wasn't the right choice. Right. In terms of open sourcing it, we've thought about doing that. It's more of an issue of having the time to actually polish the code. It's not in great, the code is not the most well documented or in great shape right now. So that's more of an issue than anything. Is I think Andres and Elizabeth and Frank wouldn't want to open source it without having polished it first, and we'll see if we have time for that. And in terms of test cases, so there was a whole effort ahead of time before the grid optimization competition to develop realistic large-scale test cases. You might be familiar with the RP grid data projects. And so this was an effort from, I forget, 5 teams to put together realistic large-scale data sets that would be representative of real systems without having the same confidentiality concerns on the data. So the competition used a set of those, some that they told us ahead of time, some that they didn't. They had held those in reserve, some in reserve. And then they sprinkled in a set of additional industry test cases on top of that were real test cases used in industry. They didn't tell us where they're from or what they were, they just gave us the size. It turned out our team actually we did really well on the synthetic cases, or relatively well on the synthetic cases. And we did less well, relatively speaking, on the industry cases, which is somewhat frustrating because I don't know what's different about them. We can't dig into them to know why. And so, I mean, we still did fine on them, but we did noticeably worse on those cases. And so there's something different about this. There's a whole effort going on right now. The folks at Wisconsin and Texas A&M have been trying to figure out how to characterize whether a test case is realistic, how realistic it is. And so I think that's all really, I saw a talk on that last week that they just put together. Really interesting work in progress. How do you characterize the realism of the test case? So yeah, sorry, does that answer all your questions?
Yeah, it does. Thanks a lot. That's great.
Cool. Okay, let me keep going. So our takeaway message from this is these state-of-the-art nonlinear solvers, you can jointly optimize real power, voltage magnitude, and security constrained open problems. I mean, hopefully we'll continue to show that in the second round of the competition, but that's what we're hoping to convince industry. All right, so that's local optimization techniques. What about approximations? There's been a lot of work in trying to approximate the nonlinearities using assumptions on typical power system characteristics. So the most famous of these are the DC power flow approximations for transmission systems. I stepped through these earlier. But there's also, you might probably familiar with the linearized distal equations for distribution systems. These were developed in the late 80s by Brandon Wu. It's a different style of approximating the nonlinearities. Basically, it eliminates the losses in, or simplifies the loss terms in distribution systems. And I'll mention there's been a huge number of alternative methods for making approximations. And so I'd refer you to, so Ian and I put together a survey paper. This took us, I don't know, 4 or 5 years to write this thing. So hopefully you find it useful, where we went through and we tried to look at all the approximations and relaxations that people have used for the powerful equations. So if you're thinking you've come up with some fantastic new powerful linearization, maybe you have, but double check, because a lot of people have done a lot of stuff. Okay, so what is the fantastic new powerful approximation that we came up with that I'm pretty sure no one's done? We've been calling this class of approximations optimal adaptive powerful approximations. And so this is work with Sidat Misra at Los Alamos and DJ, well, DJ was at PNL, and Tillman, some folks in Germany. And so the goal here was to come up with approximations that worked well over a range of power system operation. So not just, okay, how do I give you an operating point, I say, what's the best linear approximation? Well, okay, it's the Taylor approximation. We teach all second-year calc students this, right? And that's the best local approximation. But maybe I don't know what my operating point is exactly going to be because there's lots of uncertainty. Well, I'd like to construct a linearization that works well for a range of operation. One method you might do this here was we came up with an algorithm that would minimize the maximum linearization error over an operating range. So we said, all right, start with some linearization, then compute the largest linearization error with respect to that existing linearization, and update the linearization to minimize the maximum error. Okay, this is maybe better, but it's not great. So then you iterate again, compute a new worst case operating point, and update the linearization. And it turns out you can keep iterating on this. We can show that if you keep finding the worst case operating point, eventually you'll converge to the linearization that minimizes the maximum error. You can do the same thing in terms of computing linearizations that minimize expected error if you have probability distributions, or there's all sorts of different approaches you can use.
Dan, is that computationally tractable to minimize the expectation?
Yeah, so it's tricky. If you want to do it, so what we did in this, we had one paper at PowerTech where we did that using polynomial chaos expansion methods, which are not the most tractable, although CDAN tells me they're getting better. So that was limited to small problems, but there are methods, sampling techniques. I mean, this gets into all the standard, existing data-driven. CDAN tells me this is machine learning. I don't know if it's machine learning, but it gets into all these existing strategies for data-driven approximation methods that you can apply here without in a straightforward way. So yeah, the idea being that you do a bunch of computation offline, and then you try to use, I do this for maybe a week ahead or a day ahead or something, and then I use it in the hourly dispatch or something along those lines. Right. Okay. So approximations. The next topic I want to talk about and spend maybe the most time on. Oh no, I'm running out of time. Okay, maybe I won't spend much time on convex relaxations. So this is maybe my favorite topic. The idea here being that we take our non-convex feasible space, we relax the nonlinearities, and we enclose this non-convex region within a larger convex space. So here's the example I gave before. We've got this global solution, the local solution. We wrap a convex region around this non-convex region. Then we know that we can find the global solution to the convex problem. If it turns out that the solution to the convex problem is the same as the solution to the original non-convex problem, well, that's great. In that case, we can recover the original global solution. We have a certificate that we've got the best global solution. There's zero relaxation gap. It'd be great if that always happened. It might not. Here's a different relaxation where if we optimize in this direction, we have a gap between the solution to the relaxation at the red circle and the solution to the original non-convex problem at the yellow star. And so what a lot of the work in these convex relaxation ideas have been is how do we go from relaxations that look like this back to the ones that look like this? Or at least how do we tighten it? From my perspective, relaxations have 3 main advantages over local solution algorithms. So, I mean, why? Why use a relaxation? If you're not using one of these 3 features, you probably are doing something wrong. or you might be doing something wrong. So one thing it does, it allows you to bound the optimal objective value. You do get upper or lower bounds depending on which direction you're maximizing or minimizing, conservative bounds on the objective function for the original non-convex problem. It also allows you to certify infeasibility. So if the relaxation is infeasible, then the original problem is guaranteed to be infeasible. And since the relaxation is convex, you can prove infeasibility with existing methods. So that can be helpful. And it turns out that if you solve these certain relaxations, if they satisfy some checkable conditions, then you can show that the solution to the relaxation is the global solution to the original problem. And so many of these conditions have been developed at Berkeley. There's Javad and his collaborators and a whole bunch of folks have spent time on this. And so, yeah, this is really cool. Again, I point you to the survey paper if you want to know more about this whole area. What's an example of a relaxation? Oh, I want to get to restrictions. Did we stop at the top of the hour, or is it a bit long?
So Dan, we can, or you can just keep going and folks can step off as necessary. Whatever is best for you, but I don't know, I'm enjoying the talk. I imagine others are as well, so don't feel obligated to rush.
Okay, sounds good. I'll keep talking then. Okay, so what are some of the standard relaxation methods that people use? One that's gotten a lot of attention is the so-called QC relaxation. If you write out the power flow equations in polar coordinates, these are the same equations I had shown before, where we've got the voltage magnitudes and angles within these trig functions. If you look at the nonlinearities that are sitting here, really what we have is, well, we have a squared voltage magnitude, and also then we have these product terms. Voltage magnitude times another voltage times a trig function. And so really the nonlinearities are it's not like there are any nonlinearities, there are these very specific nonlinearities. And so what Carlton and Hassan and Pascal came up with, I thought was really clever. What they do is they take these nonlinear functions. So say we have the sine function, the cosine function. In reality, we have to be on this black curve, but let's say we don't. Let's construct a convex envelope around these non-convex functions. And so here, this gray region is this box-shaped gray region, and this parabola above the cosine function. They say, okay, you just have to be in this gray region, not on the curve itself. And if you have tight enough bounds on these angle differences, which you can either get or either have, or you can get them using some other computation, bound tightening methods, also some of which were developed at Berkeley. Turns out you can tighten these relaxations to be quite good. So yeah, so that's one example. There's also STP relaxations. There's a whole, I mean, you could write a 200-page paper on relaxation.
Yeah.
Yeah.
Just to chime in on the QC relaxation. I'm not sure if this is true, but my understanding from the paper is that the real power from the QC relaxation came from the fact that it can be used redundantly with standard SDP or SOCP relaxation. So basically, you just increase the number of constraints that you have on this convex set to kind of make sure it's still well behaved at the expense. So it kind of keeps it in a reasonable region at the expense of computational complexity.
Exactly. So yeah, so you can combine these things together. So if you look at, I mean, so Carlton and Hassan and Pascal spent a lot of time, especially Carlton, on this power models package in Julia. They've got this stuff implemented there. They don't actually have it integrated with an STP relaxation. There's an STP relaxation in power models, and there's a QC relaxation, but they're not intersecting in that package. I've implemented that before. It does fit together nicely. So
Carlton gave a talk last fall, actually, and it was really good. And what he said actually is that he uses just the standard SOCP relaxation for most of his applications because it's computationally tractable. And if he needs to bring in something that is more likely to provide a zero duality gap, he'll use the QC relaxation. But I get the impression that with the majority of his research, he just uses the SOCP.
Yeah, it really depends on what you're trying to do.
Exactly.
I mean, and there's many, and I think that would be one of my takeaway messages from this whole thing as well, is like, there's a whole slew of these approaches. And it's not that one is better than another, It's more of what is the right tool for your job. And in many cases, if you're trying to just come up with, so for instance, say you're just trying to figure out, which lines to focus on, and you don't need the exact answer for say some continuous variables. You just care about identifying these crucial lines. You might not need the most sophisticated relaxation to get the right answer. Now, if you're operating the system, well, okay, now you maybe need something more accurate. So you really want to tailor the tool to the job. That's important.
Yeah. I mean, I guess that's the point of your talk regarding all 4 different kinds of methods. I'll let you.
Yeah, exactly. So like for the competition, the grid optimization competition, it was sort of natural to us that local solvers are probably going to be the best way to go. But in other contexts, I'll talk about, actually, this is a good lead. I'll talk about some applications of convex relaxations and how can you use the characteristics of these various formulations in ways that make the most sense. So the one natural thing you could do is you could say, all right, let's just try to find a global solution to some problems. We're just interested in knowing what is the global solution to these, proving what is the global solution to these problems. So like it's OPF problems. So what you can do is you can take your non-convex region, you split it into pieces, and you do what's called spatial branching. And then in each of these pieces, you compute an upper bound with a local solver, a lower bound using relaxation, and you do the standard. It's very similar to mixing programming branching bound style solvers to eliminate regions where you know that the global solution can't exist. And you keep iterating and splitting these regions until eventually you get to the tight enough bound where you say, okay, we've got the global solution. So as an example, here's our non-convex region. We wrap a convex relaxation around it. If that's not tight enough, we can split the region into pieces and put relaxations around each piece. And identify regions in which the relaxation says the objective function has to be, the objective function bound tells you the solution can't be in this region. So you can ignore it and focus on other regions. And so this is, a very popular approach, standard tools in industrial engineering. So this is the natural thing to use a relaxation for. Another thing you can do is to use a relaxation to certify power flow insolvability. So this is a question that has sort of been of interest to power system engineers for a while is, well, I have some operating points. I have some load demands. I want to know, is this a feasible operating point? Can I satisfy these load demands? So what do? You go away and plug it into Newton-Raphson method. You initialize your Newton-Raphson method with a flat start, and you try to converge to a solution, and Newton-Raphson fails. So then you try again with a different initialization. You try again, and try again, and try again. Eventually, you can't find any solutions any initializations where Newton converges. It doesn't mean that there's not a solution. Maybe there is. You just had a poor initialization. Turns out these regions of convergence for Newton methods tend to be fractal. And so it's really, in principle, hard to know. A relaxation would allow you to know for sure. So this is, this fairly famous PV curve where we're showing the power demand on one axis, the voltages on another axis. And what you can often do is you can show that beyond some value of some loading demand, I can solve a relaxation to show that no solutions can possibly exist beyond this point. So I don't know how else to do that. Relaxations allow you that capability. Another approach that we've used this for is for solving robust optimal power flow problems. So if we have some uncertainty in our problem and from wind and solar generation, and what we'd like to do is to guarantee that our solution will satisfy the constraints, not just at the nominal operating point, but also for variability. We have some load variability or solar variability. And so you can imagine, here's some cartoon example where I've got the current flow on some line on the vertical axis, and I solve an OPF problem, and it schedules me right up to that limit. So that's what it'll do. It'll use the flow as much as possible, or lose the line flow limit as much as possible. But in reality, that's not the real power flow that's going to happen. Maybe I have the wind and solar pushes me around, and so I might violate those flow limits. And so what you might want to do is to say, well, how much would I have to back away from my actual constraints so that I'm sure that I choose a nominal operating point such that I don't violate the constraints when the uncertainty is realized? How much, in other words, do I have to tighten the constraints from their specified value to account for the uncertainty? What security margin do I want to impose? And so we have a paper on this, Lena Royal and I put this together in PSC, where you can compute using a relaxation, how much do I need to tighten those constraints? And so, again, I'll refer you to this paper if you want to see all the details, but I'll give this is not a cartoon example, it's an actual example. There's a 3-generator, 3-load system where we have plus or minus 5% uncertainty at each load demand. And the feasible space for the nominal problem looks like this sawtooth shape here, where I'm showing on the axes the current flowing on different lines in the system, 4 to 2 and 4 to 1. And it turns out the solution would push you, the solution to the deterministic problem would push you right up against, at this red square, at the flow limit. But then when you go actually sample a bunch of uncertainty realizations, what you see is, about half of them violate the line flow limit, which makes sense. You're perturbing your solution. And so what you can do is you can use a relaxation to say, how much do I need to back away from this? Basically what you do is maximize over the uncertainty set. How much can the flow on this line change as my uncertainty varies? And then make sure that I back off by enough so that I don't violate any of the limits when the uncertainty is realized. And the nice thing with doing this is it only uses the objective function value, the bound on the objective function, which I know is valid. I don't have to worry about the relaxation. If the relaxation is inexact, it just pushes me further away. If I don't have a tight relaxation, I just move further away from the bound than I otherwise would have to be. But fine, I operate the system a little bit more conservatively than I would have to. And I don't, if the relaxation is inexact, it doesn't hurt me that much. So we like this. This is fun. That's one example. Another problem that we used relaxations for was to certify security of distribution systems. So if I know I have some range of load variability at all these locations, can I show that that range of load variability won't lead to violations of the voltage limits or line flow limits on my distribution system? And so what we can do is you can solve subproblems where we use relaxations to compute upper bounds on the worst case violations. The worst case, how large could the voltage or the line flow at this bus possibly be over this range of variable power injections? And if the worst case thing that can happen is not so bad, if it's within the operational limits, then we're okay. We don't, that level of variability is fine. I don't even need any sensing or measurement to tell me it's fine. I know it's fine because I've solved this problem. Now that might not always be the case. Maybe there's some locations where I can't show, the relaxation shows that I might violate the constraints. And so what we're working on now is, we have some initial work, continuing work on, is to say, where could I put some sensors? Turns out in this example, if I put one sensor here at this bus 11, and if that voltage magnitude is within its limits, then I can show that for levels of variability up to plus or minus 50% or some amount of variability in the rest of the system, if this bus is okay, then everything else is okay. So what this allows us to do is to put a limited number of sensors in the system. So I don't have an observable distribution system, but I at least know that as long as all the sensors are within some certain thresholds, I won't violate the flows or the voltages at places I'm not measuring. So this is part of a PSOR project that Lena and Molzahn Hedman at Arizona State and Lena at Wisconsin and I are working on now, is to figure out what's the least number of sensors I need to put so that I can guarantee that I won't violate the constraints. Yeah. Okay, one other application. So this was with Spiros. I never pronounce Spiros' last name. Spiros at DTU and his former student, Andreas Vensky. And the idea was, my goal was to make pictures of powerful or OPF feasible spaces. Spiros wants to create machine learning data sets. And so the goal is to come up with a bunch of operating points, a balanced data set of feasible operating points and infeasible operating points, so we can go away and train some machine learning model. And so it turns out if you just sample operating points randomly, most of them are infeasible. It's hard to find feasible operating points by random sampling. In other words, the feasible spaces tend to be sort of thin in the space of loads in generator outlets. And so how can we get more balanced data sets? Well, what we can do is we can use convex relaxation. So we take our non-convex problem, we wrap a relaxation around it, and then we make projections. So we start at some random points and we make projections onto the convex space. Now this gives us hyperplanes, the normal or the tangent planes at this tangent point, or at the point we project onto. If I take a whole bunch of them, I just solving each of these is projecting onto the relaxed space. That's solving the relaxation ones. That gives me a system or a set of hyperplanes. It gives me a polytope that surrounds my non-convex region. Turns out there's efficient ways to sample points within a polytope. So you basically take the convex hull, or the convex combination of all the vertices. You can randomly choose the weights in that convex combination. You can sample points efficiently within a polytope. Then we're left with a set of points. We can solve the power flow equations at each of the sampled points. And that allows us to say, okay, is this point feasible or infeasible? And so we can come up with data sets that are not too unbalanced. We have roughly 50-50 splits between balanced or between feasible operating points and infeasible operating points. It also is very useful. I didn't actually use it to make these pictures, but it's useful for, it's much more efficient for generating these pictures than the method I was using. So you can make cool pictures. Cool. Okay. That's all I want to say on convex relaxations. Can I go ahead to convex restrictions, or do you guys have any other questions? No restrictions?
Yeah.
Okay. All right. So what is a convex restriction? This is really cool work. There's a whole body of work that folks have done with this. A lot of it's been at MIT with Kostya Tritsin's former group, some of the folks at EPFL, at Mario Pollone's group. Who else? DJ has done work on this. This has been a really cool topic. And so the goal is, if I give you, this is sort of the converse of a relaxation. I give you some non-convex feasible region, and I give you some points inside that non-convex region. I say construct a convex region that's completely enclosed within the non-convex region. All the methods that people have developed so far are based on fixed point theorems, like Brouwer's fixed point theorem is pretty popular. And these are all dependent on a base point. So if I choose a different point at which to construct this restriction, I get maybe a different restriction. So here's some examples. Turns out, so I'm going to skip the math here, but one of the points that I talk for a whole hour on the math behind these things. But one of the points that I would emphasize is this, it's a nice picture, right? It makes a lot of sense. I take this point, I expand the space inside. But what gets really tricky when you try to do this is in the OPF problem, or power system optimization problems, we have equality constraints. So we have some equations that have no interior, there's no volume. And so how do you construct an interior, a restriction of a region that has no volume? That's not so obvious what that even means. Like, how do you define that? And so what people do in this case is basically what they say is they want a projection. They want to show that they project out some of the state variables, and they want to show that the projection of those equality constraints onto the control variables, that has volume. And they show that they try to construct interior regions of that projection. So even defining these things actually turns out to be non-trivial. So without going into any of the math, I'll show some applications because I can make pictures of the applications. Sorry, this slide always takes forever to advance. There we go. Okay, so one application. This is work with Lena at Wisconsin, Kostya, and so Kostya's student Dongchan. Really, all the credit should go to Dongchan. He's done fantastic work. He's graduating soon. If you're looking for a postdoc, I think he's probably done it in a year or two. He's done really cool stuff. And so one application we were trying to use these convex restrictions for was to construct what we were calling feasible paths. So start at some operating point. That's the red dot here. And I have some desired operating point I want to get to. And I want to construct a way to get there without violating any constraints. Where this is tricky is, well, this is a non-convex region. I might have holes in the middle or other non-convex. And so if I have this initial operating point, my desired operating point, if I just tried to directly go there, I'm going to violate some constraints along the way. Maybe I don't want to do that, especially if they're big constraint violations or would trigger the protection systems. This is more relevant as we get more renewables, and I'm spending most of my time transitioning between points, not actually at some point. So how do I do this? Well, what I can do is construct a convex restriction around my initial point. And then I can try to get as close as I can within the convex restriction to my desired point. That turns out to be this blue circle. And then I move there. And I know, because this is a convex region, that all points along this linear path are also in the convex restriction and therefore are in my original feasible set. So then I iterate. I use that as my new base point. I construct another convex restriction. I move as close as I can over there. And then I do the same thing. I construct another convex restriction. You see the restriction itself in green changes as the base point changes. And that's why as I move around, I'm able to, hopefully get to my desired points. And that gives me a piecewise linear path along which I'm guaranteed that all the points on the path are feasible. This doesn't always converge, might not converge. But at least it does, if it does converge, it gives me guaranteed that that path is feasible.
So Dan, this is the trajectory of the optimization point, essentially.
So this is the trajectory. So there's two ways to interpret this. One is that, yeah, if I'm trying, I could use this just to minimize cost. I could say, I don't know what my desired point is. I'm just going to construct a restriction, find the lowest cost points, compute a new restriction, construct the new lowest cost point. I just move. And then, yeah, it's the iterations for the algorithm of solving the OPF problem. But that's one interpretation. Another interpretation is if I know where I'm going, I've solved an OPF problem for 10 minutes from now, and I want to get there. I'm not at that point yet. So then I'm going to try to transition from my current operating point to my desired operating point. And that transition might lead me to infeasibilities. So I could tell the generators to not directly go from, don't just ramp up linearly to that point. I could say, start off slow, then speed up, then slow down, then speed up and slow down to get to that point.
So that's more of a classic reachability interpretation where you are literally optimizing over time to not cross any infeasible operating points. Whereas the first one is just using this iterative concept to inform the optimization, basically.
Right. Exactly. So, and both have valuable interpretations. The first one can be like, if I want an operating point that I know I can get to, I'm like, for instance, in this Nike swoosh feasible space, this is one of the, so Patrick Fantasy at our team took that 5-bus case and he put a standard, generation control, their RTE's standard generation controller on one of the local solutions. And he said, drive it to the global solution. And it wouldn't go, it didn't work, which sort of makes sense because it's doing something weird in between. And so if you want to sort of have a guarantee that the solution you get, you can actually achieve, you can actually reach, then maybe you don't care about finding the global solution. You want to find the best point that you can reach. And that's where something like this might be more valuable.
Yeah, that's related to the kind of online optimization literature. In terms of, if you're running the optimization offline, and you don't have ramping constraints. The premise of I guess quasi steady state optimization is that you could jump there, but it depends on the ramping constraints.
It really depends on the dynamics, and you're not modeling the dynamics, so you don't know.
Exactly. So probably, especially with the power system, not a good idea to just jump there.
Yeah, they do it now. Right now, this is just not a problem in the DCOPF at all because you can't have holes in your feasible space for the DCOPF. So this is just never an issue.
So they will
yeah. It doesn't mean it's not actually an issue. It just means we ignore it.
Yeah.
Yeah.
Okay.
Cool. Okay, let me give one other example, and then I think I'll probably be almost wrapped up. So another way that you can use, so I talked about robust optimization earlier using convex relaxations. Turns out you can also use relaxations to solve robust optimization problems with convex restrictions. And so this is a cartoon example, but it's what's actually happening in the systems. Again, this is Dongshan's work, really cool. And so if you imagine, here's on one axis, I've got my control variables, my generator output, or the nominal generator output. And then my vertical axis, I've got the uncertainty, say the demand, and some uncertainty. And in blue here, I've got my feasible region in terms of these are all the points that would satisfy the constraints in the problem. And so what we can do, we want to solve a robust optimization problem. And so if I had just some nominal points, then my task would be simple. I can, if this was my load, I could pick any points between this minimum and that maximum value, and that would satisfy the load. Now you could use a convex restriction to do this. Construct this green region, and here's my convex restriction. And so then we'd say, okay, we just have to pick between these green bars. Any point between there would satisfy this one nominal load. But what happens if I don't have a single nominal load? Maybe I have an uncertainty set. I want to be robust to all the realizations of uncertainty within that uncertainty set. And so then I'm really going to restrict myself further of what operating point, what generator outputs, what control variables I can choose. If I want to be sure to satisfy any load realizations within this range, what I really need to do is make sure that I'm within this range here, the red dashed lines. And so we're calling these robust convex restrictions. In other words, a convex region within which any operating point, when perturbed by a particular uncertainty set, will stay within the convex restriction or within the screen region. And so this is useful. Then I can pick, if this is the lowest cost operating point within this convex restriction, I can solve a robust ACOPF problem. And I'm guaranteed two things. One, that I satisfy all the inequality constraints for any realization of uncertainty within this uncertainty set. And two, that I actually have a powerful solution. That's really been at least a conceptual challenge with robust AC problems, is I can end up with uncertainty realizations for which no power flow solution exists. That's really bad. I don't want that to happen. That means my system's unstable for that uncertainty realization. But I can't find it, right? How do I search for, if I optimize over a problem where I have the power flow equations as constraints, well, I'll never find a point that doesn't have a power flow solution. So to ensure that the problem is truly robust, that it has an AC power flow solution for every uncertainty realization, and that AC power flow solution satisfies all the inequality constraints. This is the only way I know how to do it, is to use these convex restrictions. Turns out there's another interpretation of this. If you kind of project on the other axis, what you can say is we're looking for any operating point so that when I project the convex restriction, that I enclose the this entire uncertainty set. So here, if I look at this operating point, this particular value along the x-axis, and I project it onto the y-axis, I get this green region. That green region includes the uncertainty set. And so here, this is a robustly feasible point. There's two sides of the same coin as to how do you interpret this. And so this is my takeaway message from this one. And as far as Lena and Dongchen and Christian, I can tell, this is the first algorithm that can provide robust feasibility guarantees with respect to both the AC power flow equalities and the engineering inequalities. And there's no requirements on any particular power system model. It doesn't have to be radial, or there's no restrictions on what you model. And so we're excited about this. This is a cool algorithm. Dongchen did a great job.
And the robust is basically the load could be anywhere between these bounds, essentially, and you can be sure that you will be, and it doesn't take into account a -1 robustness.
Right, it's not, yeah, this is complete. So actually that is an interesting question, is how much does ensuring N-1 robustness also ensure robustness to this, or vice versa? That is unknown, as far as I know.
And how much can you control the convex restriction set? Is it basically like mathematically you're drawing on the state space, the feasible set in one way or another, or is it like you pick a point and an algorithm kind of expands from there?
Yeah, so it's the algorithm picks it. So, or you pick a point, and the algorithm, basically Dongchen has this really clever method of sort of coming up with a set of convex constraints. I mean, you don't have to even define the only thing in the robust case that you have to define is the uncertainty set. Just, you can define any ellipsoidal uncertainty set. And he tells me any norm is fine. Any well-defined, an uncertainty set defined by any standard norm is fine for the uncertainty set. But for the convex region itself, there's no, his algorithm just generates a set of convex constraints. You don't have to pick like a box or something like that.
Could you? Like, do you get to pick a box if you wanted to?
Probably. I bet you could do that. Yeah. I mean, certainly you could take this convex set and then inscribe a box into it.
I was just going to say, in the Berkeley convex optimization class 227B, we tried to do robust OPF, and kind of classic robust OPF analysis is really restrictive in terms of the problem model. So you have to use linearized power flow, and I think, if I remember correctly, box constraints on the uncertainty. And if it's there, you can kind of feed it through these cool algorithms. But if it doesn't fit there, you're kind of dealing with non-convexity and totally out of luck.
Yeah, and that's why I'm excited about this stuff. Is the existing methods for robust optimization are really limited. You need linearity and you need some restrictive uncertainty sets. like an ellipse, or I think you can get away with ellipses in a linear case as well. But yeah, and we're still restricted on the uncertainty set, but I don't know, ellipses are pretty general.
Yeah,
But
really,
dealing with the non-convexity is, I don't know of any other way to do it. It's clever.
that's really cool.
Yeah, and again, I got to give all the credit to Don Chan. Like, he came up with this method. We helped him apply it, but this was really his ideas. So it's a neat approach. Yeah, so I think that was it. That's all I was going to talk about. But so, okay, we have 4 methods for dealing with powerful nonlinearities. There's local solution, there's approximation, there's convex relaxation, convex restriction. And yeah, this, to your point earlier, they're useful for different things. So, I mean, sometimes I've had students ask me, okay, so what's the best approximation? What's the best relaxation? And the answer is, well, that's not really how it works. It's what's the best for your application. And you can see here how we use different approaches for different problems. So yeah, check out my survey paper. Hopefully that's useful. It took a lot of time to write, so hopefully you guys read. Yeah, I'm happy to stick around and answer questions.
So that was wonderful. Thank you so much, Dan.
Yeah, thanks.
I've been kind of bugging you with questions throughout, so I'll open up the question section to everyone else first, essentially, and ask questions only if no one has anything to say.
Oh, and I think there's people in the chat asking stuff. Cool. Should I answer these, or what? How do you want to approach this?
Yeah. Why don't we start there? I mean, I kind of asked Johnny's question reminiscent of a reachability problem, which is, yeah, in fact, it is true reachability in one application and reminiscent in the other. And then Richard's question, can you run the path in reverse as well? I don't know if Richard's still on the call though.
Yeah, I mean, so it's really just any 2 points. Give me 2 points and we'll see if we can connect them. And I will mention here, so it's similar to a reachability question. It's not exactly the same because we're not considering any dynamics. It's all steady state. If you wanted to build in the dynamics, that would be an interesting problem.
Hi, Prof. Molzahn. Thanks for the talk. It's really fantastic. I wanted to ask 2 questions. I guess like 1 question really, but like, for example, in like these 4 figures that you have on the last slide, you know, both the convex relaxation and the approximation can result in like points which aren't physically feasible. And so like my first question is how is that dealt with? Like, do you just like realize that it's feasible and like solve it again? And like regarding for instance, like the local optimization, which you said that a lot of the teams on the grid optimization competition were using, like, are there ways to guarantee or like that, you know, maybe you can come up with some like bound on like how close that is to like the actual global optimal? So yeah, those 2 questions.
Right. No, those are both good questions. So in terms of your first question with relaxations and approximations, yeah, you might end up with an infeasible point. In fact, you often do. And so there's, I guess, a couple answers. If you look at it from an industry perspective, they do this today, is they solve DC part flow and it doesn't satisfy. In fact, I think Kyrie Baker at C Boulder has an interesting paper on showing that DC approximations almost never give feasible operating points. And so this is where, if you're an engineer and you go, so one perspective, you go work at MISO or Cal ISO or wherever, and you get paid a bunch of money to figure out how to do this. And in fact, oftentimes it's more so than even just this issue. It's how do you make sure the dynamics are okay? And how do you make sure that, you know, there's enough reactive power margin and all these other considerations that they make. It's much more involved than just making sure that it's AC feasible, but AC feasibility is a part of it. So yeah, I mean, one answer is you got to know the system really well and you figure out how to do it. The other answer is there's also methods that people have worked on. The more research answer is, you know, how do you modify the relaxations or modify the approximations to take the solution and try to get back to something that is feasible. The folks at Berkeley and other places, Javad and other folks have worked out interesting penalization methods to try to push the solution back towards a feasible operating point, and that's really cool work. Other things you can do is try to use the solution you get as an initialization for a local algorithm. Andres Spensky and Spiros and I have a paper on that. It turns out it's hard because the interior point methods don't use that initialization well. And so, and interior point methods are also really fast. So it's hard to beat them if you're solving relaxation first and then using it as an initialization. It might be doable. And I think there's maybe some meat there left on that bone, but it's not straightforward. Then that was one question. You asked about local solve. What was the question about local solvers in the competition?
Like how can you, like are there theoretical guarantees to see how close you are to the global solution?
Yeah, so the obvious thing to do is just solve a relaxation of the problem. Now that gets tricky because in the competition's formulation, let me go back. They have these complementarity constraints where you have this PV PQ switching style constraints. I'm sorry, this is I'll lock up my computer. And those are somewhat difficult to relax, but I talked with Andy Sun about this, and he mentioned that they had tested a handful of the test cases from the competition. We didn't look at whether it was global or not. Turns out there wasn't a lot of time to do everything you need to do for this competition. But Andy indicated that, yeah, most of the time with some simple relaxations, they were getting pretty good bounds. So I suspect we probably were getting the global solution. We were probably getting the global solution with respect to the AC power flow nonlinearities. Whether or not we had all the right contingencies or not, that's a different story. Yeah. Does that answer your question?
Yeah, thanks a lot.
Can I ask a follow-up to the first question that Gabriel asked about the feasibility of the solution of DCOPF?
Yeah.
You mentioned briefly in your talk that there are industry practices for incorporating losses and other tricks of the trade. Do you have a resource that might explain how that's done?
So the best, most accessible paper I know of on that is there's one by Brian Stott. So Brian, in case you don't know, Brian Stott is one of the giants in this area from the 70s and 80s, who's developed a lot of the methodologies we use today. I
read his Revisiting DCOPF paper.
Yeah, that's what I was going to suggest. Now, I think you could also dig into the operating manuals for the ISOs, and you could probably find it in there. I've never looked, but I've talked with some friends who work at ISOs, and they say it should be there and that there's all sorts of stuff they do.
Probably light reading.
I wouldn't, read Brian's paper first.
I've wondered about that in the context of locational marginal prices, because if you don't take into account losses with locational marginal prices, the market operator can actually be insolvent because they're selling less power
than they produce. Yeah.
Yeah. So it's a super interesting problem, something I've looked into.
Interesting. I hadn't thought about that specific problem, but yeah, I mean, there's a lot of things that work well in theory. And then when you go see how they actually implement things, I mean, for instance, when it comes to pricing, right? They need a feasible problem. The problem can never be infeasible. And so what they'll do is they'll penalize constraint violations, and that's the grid optimization competition. That's what it does too. And so, but then what does that mean for your dual variables, right? If I add a penalty term to the objective function, that's really big. My dual variables get all messed up. They don't actually represent the marginal cost of generation anymore, but that's what they do. And then somehow you have to massage those.
Shouldn't those basically, if the problem's simplified enough, settle down into the appropriate price for losses, price for a constraint? That's like where the LMPs come from. I guess if you have an approximation, then it becomes problematic. But.
Well, so where you run into trouble is, so how big of a penalty? So I can raise the prices sort of arbitrarily high by increasing the penalty on the constraint violations, right? So if I have soft constraints, what does that mean for prices? I mean, maybe there's a good interpretation of it, but
that's what the LMP is. Like, dual ascent should find the exact right price so that you just barely don't violate that constraint, and then you charge whatever nodal price results from that.
Right, but I think, I mean, maybe I've not actually worked in this area, so I might be making this up, but I think if you, at least this is what my friends at MISO had told me, is that like, if you double that penalty, right? I have a penalty in the objective function that says, how much do I care about violating constraint versus how much do I care about, what's that?
Just double arbitrarily.
Yeah, I just make it down twice as big. Then now my prices, they certainly change.
Yeah.
And so what is the right price? Well, it depends on what the penalty is and who picks the penalty. I mean, I don't know, it's a number.
Well, we have some good questions in the chat. I'll let you read them.
Sure.
Start with Sam.
Okay, so Sam says, yeah. Oh wait, okay. Let me read this more carefully.
Or I can read it out loud also.
Sure, yeah, why don't you read it out loud? Because I don't think it gets recorded.
Exactly. So I'm wondering if it's appropriate to ask you to provide a very intuitive non-mathematical sense of assigning the quantitative measure of the quality of an AC OPF solution from SDP relaxation using a transformation of the mesh network to an equivalent tree.
Is it appropriate? Maybe. Let me think about this. So so maybe you can do, maybe Sam, what you're talking about is where you're talking about these chordal extension ideas where you kind of group the nodes together and make a chordal tree out of it. Is that for the SDP problem?
Yeah, exactly.
Yeah. What's the mathematical sense or the intuitive non-mathematical sense? Yeah. Okay. So here's how I solve it, interpret, right? So if I've got two locations in the system, in the SDP relaxations, which I haven't talked about explicitly in this talk, but SDP relaxations basically relax all the products of the voltages. So I have V times V conjugate, V1 times V2 conjugate, V1 times V12 conjugate. I have all the voltage products in my formulation. And then what the SDP relaxation does is it relaxes those by lifting the product variables to a matrix variable. And then it makes the that matrix, if it were rank 1 in positive semi-definite, then that's equivalent to the original problem. And so what people do is they relax the rank constraint, they just drop that and then get a convex problem. And so if you just do that naively, what you have is one big matrix that has all the possible products of voltages in the system. And so as you might imagine, most of the products in that matrix, you never use. If I don't have a connection between bus 1 and bus 7, I don't care about the product of V1 and V7. All I need in the SDP relaxation is there to exist a value for that entry in the matrix so that the matrix overall is positive semi-definite. Otherwise, it doesn't appear anywhere else in the problem. And so what these sort of chordal decomposition tree, chordal tree approaches do is that it effectively takes advantage of that fact that we don't need all the products. They don't show up everywhere else in the problem. And it turns out by this nice theorem by Groen, you might have heard of matrix completion algorithms or matrix completion methods. There's a matrix completion theorem that says if I have a matrix where I have a bunch of unknown entries, and I just want to choose them, I just want there to exist a choice for those unknown entries so that the overall matrix is positive semi-definite. I don't have to solve a semi-definite problem for the whole thing. That'd be what you naturally do. Instead, what you can do is say, I can break this big SDP constraint up into pieces, and I just need to make sure that certain pieces of this big matrix are positive semi-definite, and that's enough to guarantee that there exists some value for these unspecified entries that will make the overall matrix positive semi-definite. So it's based on a matrix completion algorithm. You've probably heard of matrix completion in the context of rank completion. This is positive semi-definite completion. So Sam, I don't know if that answers your question, but it allows you to break big matrices down into small matrices, which is good.
Yeah, no, that's good. Appreciate it.
Yeah, I don't know if that was exactly your question because you're talking about the quality of the solution. I mean, if the relaxation is exact, it doesn't, I think you can show a one-to-one mapping between the chordal extension and the first order SDP relaxation. Turns out there's generalizations of these SDP relaxations to hierarchies of relaxations, moment sum of squares stuff by Lasserre and Pablo Carrillo. It turns out in those cases, decomposition does matter. You don't get the same quality of relaxation depending on which chordal decomposition you use. But that knowing what makes a good chordal decomposition for these more higher order moments, some of the squares relaxations, that's not so straightforward. I don't know how to do that. If that's more of an
One of
answer.
the things that I wanted to gather from your response is that this particular method of assigning, some numerical measures on the quality of the solution is relevant, or it works out only if you're following the SDV relaxation. Like this doesn't work for SOCP approach or some of the other approaches.
Right. This is the challenge that you have with these relaxation methods. Is oftentimes basically what we know. This is maybe a bit of a strong argument, but basically what we know is that either it's exact, in which case we can show it's exact, it's tight, done, global solution, or we know nothing. It could be sort of arbitrary. I don't know about arbitrarily bad, but it can be bad. And it'd be nice to have something in the middle. But I don't know of anything really. I mean, oftentimes it works well, but that's not that's a pretty hand-wavy statement. Does that make sense, Sam? Does that answer your question?
Yeah, it does. Thanks.
Cool. Okay, and then Han asks, interested in the computational complexity of convex restrictions and whether there's a trade-off between the volume of a convex restriction and the computation time. Yeah, so this is a good question. So it turns out that the way that they formulate these convex restrictions, let me see if I can advance here by enough. More so than the difficult, sorry, let me just advance. Sorry, I have too many animations. There. Oh, this is exactly the side one. Yeah, so there's a ton of papers on this, right? This goes back to like 2015. There was a lot of work on this stuff. And a lot of what people were doing was, when you look at the very first papers by, it was Hung, Nguyen, and Kostia's group, those very first restrictions were tiny. You could show like, I got some operating point and some very small ball around it was feasible. And then over this course of all this work, what people were able to do is to grow those convex restrictions to be much bigger. Let me see if I actually have a picture of some of them. Here's an example, sort of. This isn't exactly what I was hoping for. But I mean, you can see that they can be pretty big. They started off being pretty small, but they can be pretty big. Now, that doesn't necessarily come with a higher computational cost. They just came up with better methods for characterizing the region and constructing their convex restriction. Turns out the way that they're formulated as systems of convex QCQPs, quadratically constrained quadratic programming constraints. So they're actually pretty tractable. You could throw it at Mosaic or Cplex or something like that. They're not SDPs. And the computational effort involved in solving them, I don't know if, I mean, they came up with really clever ways to basically deal with, let's go back. It's in some ways deceptively similar to this QC relaxation idea. It's not the same thing because it makes my head hurt every time I try to switch from one to the other. But what they do is they look at each of these sort of prototypical nonlinear terms. So you have this, and they look at polar coordinates, or at least that's the formulation that Don changed. He's got a voltage magnitude, and a trig function. And what they do is they come up with, in the same way that Carlton and Hassan and Pascal came up with these convex envelopes. What they do is they come up with concave envelopes. And it turns out these concave envelopes are key to making the whole machinery of these convex restrictions work. And so it really flips this convex relaxation idea on its head, where before you're trying to make convex envelopes like these parabolas and these boxes, what they have to do is they have to construct concave envelopes. And then they use basically the corner points of those concave envelopes in making the restriction. And so the quality of the restriction is much more dependent on the tightness of those concave envelopes. And if people can come up with better ways of making concave envelopes, maybe they might be more computation intensive to construct, but the envelopes that Dongchen has now, they're just QCQBs, or just they're QCQBs. I don't know, Han, I don't know if you're still here, Han. Does that answer your question?
Yes, it does. Thank you very much.
Cool. Yeah. So if you're tired of thinking about ways to tighten convex relaxations, if you want to expand convex restrictions, think about how can you come up with concave envelopes, which is weird. It just makes me, all the intuition I have for what to do in those cases sort of doesn't fit well. So yeah.
That's really cool.
Yeah, it's neat work. It's been a really interesting, it's been fun watching that work evolve. We've just tried to use it.
So we're reaching the end. I do have one final question I think I would be timely to bring up. Julie, I don't know if you're still on the call, but in regards to the effectiveness of the local optimization techniques that you presented, Julie, who's one of Javad's students, recently published some work.
Yes, I think I've seen this paper.
To time series optimization problems, and really fascinating results about basically the backwards region of attraction for the global optimum based on initializing each subsequent time series optimization based on the point found at the previous optimization. And I'll let Julie kind of take it from there. But I don't know, I was interesting based off what you were saying about the effectiveness of the local optimization, and I don't recall if Julie's work required IP-opt or any sort of specific engine. So I just thought it was an interesting confluence of papers.
Yeah, I think you summarized it well, Keith. Thanks. Yeah, we used actually sequential quadratic programming because one of the kind of key requirements of our approach was that you could initialize at the solution from the previous time, which is typically infeasible for the next time. So in that sense, we didn't use IP-opt, but yeah, just one of the things we found is, you know, when you're looking at a series in this case, a lot of times it's dominated kind of by the easiest problem in the middle. So if you have a lot of hard problems, but at one time you're able to find the global, often you can kind of track it.
Yeah, which is, it's clever. I mean, it reminds me a little bit of, so there was this, so I should say, Julie, I think I'm like 90% sure I read your paper, or at least I think you gave a talk at Los Alamos, right? At the Winter Grid School? No?
No, I didn't, but yeah, it wasn't me.
Okay, I remember seeing this work somewhere and I thought it was really cool. So congratulations, it's nice, it's nice paper. And yeah, it's interesting. I mean, it reminds me a little bit of so there was some work by, it's like Emiliano Dalinas. I saw Emiliano's coming to give a presentation for you guys at some point here this semester. And they were doing some sequential convex approximation. Basically, they do this difference of convex programming idea where you split the non-convex constraints into a positive definite part. You have a matrix that represents the quadratic. You split the matrix into a positive definite part, negative definite part, then you linearize the negative definite part, and you iterate on solving convex QCQBs. And they found that at least seemed to work pretty well. I almost wonder if maybe there's some relationship between, you know, once you sort of get on the right track, it's easier to stay there. Yeah, it's cool. I think we just don't know enough about this stuff. So I appreciate you thinking in this direction.
Great. Well, unless you have anything else to add, Julie. So Dan, you've gone way over the time that we asked for, so thank you so much. That was a really good talk.
Hopefully I stayed interesting to folks.
No, absolutely fascinating, and I'm looking forward to reading the papers that you mentioned. If you could send me the slides, I'll post them online, and then also Gabriel and I will, I guess, patch together the recording and put that online as well. My internet went out, which was, I guess, a COVID disaster that people are perhaps familiar with, but anyway, it worked out. So thanks for fielding that, Gabriel.
Yeah, my pleasure. Thanks a lot, Professor Molzahn.
Yeah, no, it's good catching up with everyone. Like I said, it's really nice seeing some friendly faces on the call, and yeah, hopefully be able to make it out there before too long. We're thinking about taking the train out there this summer, actually.
That would be really cool. Pending vaccines, that would be great.
yeah.
So we'd absolutely love to host you again. That was an excellent talk. So we'll be in touch, and thank you so much.
Cool. No, thanks for the invite, Keith. And nice seeing everyone. Talk to you later. Have a nice rest of your day.
Bye.